Good evening, Nivedita and Nitish. Uh, so, please respond. Okay, I'm sharing my screen. Please tell me whether the screen is visible or not. Is the screen visible?
Yes, sir.
Okay, thank you. Okay, so let's start. Uh, this particular session is dedicated to the content relevant to the week 7 on the NPTEL course on fluid mechanics. As we have already gone through the lectures, you must have seen that the week 7 was mainly dedicated to the dimensional analysis, and which is a very important chapter. Okay, and why it is important? Because in different exams, including competitive exams, we can expect a lot of questions, and this chapter, compared to the other chapters in this course of fluid mechanics, is relatively easy, and you can definitely score very good marks in this chapter. Okay, so anywhere you go, the most important question that will be asked, means in almost all the cases, is from Buckingham Pi theorem. So Buckingham Pi theorem, it's a very important theorem. However, sometimes I have seen that there are some confusions. Okay, so before going to the problems for this particular dimension analysis, I have tried to summarize Buckingham Pi theorem. So Buckingham Pi theorem, what does this theorem states? This theorem states that if sorry, if there are n number of sorry, if there are n number of primary if there are m number of primary dimensions involved in a problem. Now suppose we have a problem. Okay, now suppose we have a problem where uh, there are n number of variables. Okay, where there are n number of variables. Now n number of variables, by variables we mean both dependent as well as independent variables. For example, suppose say Reynolds number, we know that is a function of density, velocity, some length, and the viscosity. Okay, so say these are all variables. Okay, so these are all variables. Even this is a variable, this is a dimension, means this is a number. Or let us say drag force FD. So FD is basically a function of the projected area A. Okay, the density rho, the velocity V. Okay, so in this particular problem we have seen that how many variables are there? 1, 2, 3 independent variables and 1 dependent. So the total number of variables is 4. Now, if you look at Buckingham Pi theorem, what does it state? It states that if there are n variables which are controlling a physical phenomena, and out of these n variables there are m primary dimensions. Okay, now what are primary dimensions? Now in fluid mechanics, okay, in fluid mechanics, now primary dimensions or the fundamental dimensions, we know that there are 7 fundamental units. Okay, SI units. However, in fluid mechanics, the most fundamental dimensions that we come across are m, l and t, that is mass, length and time. Okay, from a civil engineering point of view, if you think, there are 3 primary dimensions, m, l and t. Okay, so a problem which involves n number of total variables, okay, including both dependent and independent variables, and there are m primary dimensions or fundamental dimensions. Okay, so that particular system can be described by n minus m number of dimensionless groups, which are known as pi terms. So this is basically the statement of Buckingham Pi theorem. So the first statement is that there are n number of variables. There are n number of variables. Okay, so there are n number of variables, and out of this n number of variables, okay, these variables are basically described by m number of primary or fundamental dimensions. Primary or fundamental dimensions. Now, what are those primary or fundamental dimensions? These are mass, length and time, that is m, l and t. Now, in that case, the entire system can be described by n minus m. Okay. So, if suppose there are 10 variables and m is 3, so it can be described by 7 number of dimensionless groups, okay, which are known as pi term. Secondly, when in the execution part or in the application part, there are you have to select m number of repeating, okay, you need to select m number of repeating variables, okay, m number of repeating variables, and the remaining variables that you have, okay, out of this, that are used for forming or formulating the dimensionless groups. Now, it is very crucial that how to select out of the given n number of variables, which m number of variables can be decided as the repeating variables. Okay, so there are some rules. Okay, there are some rules, uh, and sometimes in some problems you may find that there are more than one variables or more than m number of variables which satisfy this criteria, but still, as a basic rule, you should remember these three. These m number of repeating variables must have among themselves all the basic dimensions involved in the problem. That is, the basic dimensions of mass, length and time. You have to select the repeating variables, m number of repeating variables. Okay, so m number of repeating variables, m is the number of primary dimensions and number of repeating variables is same as that of m. So these repeating variables must contain in themselves all the basic fundamental dimensions. The dependent variable, okay, it is very important. The dependent variable, you must not choose a dependent variable as a repeating variable. For example, just the case we have seen, say the drag force. Drag force is a function of, say, density, projected area and velocity. Okay, now you never select the dependent variable, that is the FD. Okay, you never select the dependent variable as the repeating variable. That is rule number 2. And rule number 3 is usually a length parameter such as diameter or head, etc. A typical velocity parameter, okay, and fluid density. Now, if in a particular system you have seen that there is a typical length parameter, a velocity parameter, and a density parameter, then these three, okay, can be chosen as a suitable combination for repeating variables. Okay, now let's see if length, you have selected one length, so length contains L. You have selected one velocity, so velocity is L t minus 1, so time is also exhausted. And you have selected density, so density is M L minus 3. So basically, if you select a length dimension, a velocity dimension and a density dimension, then the the first rule, that is all the three fundamental dimensions M, L and T must be there. Okay, that rule is satisfied. Okay, however, there are situations where you may not get this thing. Okay, but uh, let's see. Okay, so for the first problem is not related to Buckingham Pi theorem. It basically checks your basic idea of dimensional analysis. Okay, so Manning's formula for velocity of flow in uniform flow in open channel is written as V is equal to 1 by n r to the power of 2 by 3 s to the power of half, where r is the hydraulic radius, SO is the bed slope, and n is the Manning's roughness coefficient. You have to determine the dimensions of m. Okay, now while determining the dimensions of m, this particular question is a very simple question which uh, basically, sorry, which basically requires the fulfillment of principle of dimensional homogeneity. Now, can you tell me what is the principle of dimensional homogeneity? What is principle of dimensional homogeneity?
The dimensional formula of LHS is equal to
Yeah,
RHS
yeah,
of
yeah.
dimension.
Yes, the final dimensions or the dimensional formula of the left hand side and the right hand side must be same. So this is the fundamental idea of dimensional analysis. Okay, suppose you have an equation. The final dimension or dimensional formula for the left hand side and the right hand side must be same. Now in this equation, forget about what is the physical significance of this equation. Okay, as it is written that it gives the velocity of flow, uniform flow in open channel. Okay, but from the dimensional analysis point of view, our concern is this is particular velocity. Okay, so the dimension is lt minus 1. Okay, r is given as hydraulic radius. Now hydraulic radius, so this definitely has some length dimension. And slope, so what is the dimension of a slope? What are the dimensions of a slope? Slope, the dimensions are m0, l0, t0. Means slope is basically a number. Okay, it is a ratio, so there is no unit or no dimensions. Okay, now for this particular question you have to find the dimensions for this n, that is the Manning's roughness coefficient. So please try this problem and tell me what is the answer.
Sir, L minus 1 by 3 T1.
Okay, let's see. L minus 1 by 3 T1. Yes. So basically n is equal to, from that equation we can get n is equal to r to the power of 2 by 3 S0 to the power of half divided by V. Now for r it is L. S0 there is no dimension and V is LT minus 1. So after suitable simplifications it is L minus 1 by 3 T. So why this problem is important? This is a very simple problem, but the intention of keeping this problem in this live session was to make you realize of the fact that the dimensional analysis, the fundamental idea is the principle of dimensional homogeneity. Now let's move to the next problem. The drag force Fd on a sphere in a laminar flow is known to depend on its diameter d, flow velocity v, density of fluid rho, and coefficient of viscosity mu. Obtain an expression of Fd using Rayleigh's method. Okay. So in the question, it is given that the drag force Fd is basically a function of, the diameter of the sphere d, then the flow velocity v, the density rho, the coefficient of dynamic viscosity mu. Okay, coefficient of dynamic viscosity mu. And you have to obtain an expression for Fd. You have to obtain an expression for Fd in terms of dv, rho and mu using Rayleigh's method. Now what is Rayleigh method? Rayleigh's method is basically another important method. Now it is basically, if suppose there is a dependent variable, say a dependent variable a is there. Okay, say dependent variable a is there, or let us consider the same problem. Okay, let us consider the same problem that Fd, in this case Fd is basically a function of uh, velocity v, the diameter d, the density rho, and the coefficient of viscosity mu. Okay, now what does it mean? It means that Fd can be written as that, as it is directly proportional to v to the power of a, d to the power of b, rho to the power of c, mu to the power of d. Okay, so Fd can be written as a function of v raised to the power of a, d raised to the power of b, rho raised to the power of c, and mu raised to the power of d. Okay, now we know the dimensions of force, that is drag force F, d is known. The dimension of velocity is known. The dimension of d is known. Dimension of rho is known. Dimension of mu is known. Okay. Now, if all these dimensions are known, then what you can do, this constant of proportionality can be replaced by a equal to sign, provided we multiply it. This directly proportional sign can be replaced with a constant of proportionality k. Then this becomes an equal to. Okay. Then this becomes an equal to So is equal to k v a v raised to the power of a d raised to the power b rho raised to the power c mu raised to the power d. Okay, and this is equal to fd. Now the dimensions of fd and all the other variables are known. K is a constant of proportionality, so it is a number, basically a real number, and hence the dimensions are m0, l0 and t0. So basically what you can do is for force, what is the dimension of force? The dimension of force is m l t minus 1. Dimension of k is not required. For v it is l t minus 1 a. For d it is l b. For rho it is m l minus 3 c. And for mu, what is the dimension of mu? Mu is Newton second per meter square. Okay, Newton second per meter square. So force m l t inverse into t by l square. So these two will go. So it is basically m l minus 1. So m l minus 1 the power of t. Okay, so this is the idea of Rayleigh's method. But you please solve this problem and tell me what is the dependency or expression for fd. But before that, let me ask you one question. If Rayleigh's method is there, what was the necessity of Buckingham's pi theorem, or why Buckingham pi theorem is so popular? Buckingham pi theorem is popular because see, in this problem the number of variables, okay, even in this problem you might face some problem. If you sit and if you solve this, you will get what is the problem. But consider a problem where say f1 is a variable which is dependent on say n number of variables. Okay, say it is dependent on n number of variables, a1, a2 up to an. Okay, it is dependent on n number of variables, and this here n is say greater than 100, suppose. So it is, there is a problem, a physical phenomena, where a particular physical quantity of interest f1 is dependent upon n number of quantities, okay, and where n is greater than 100. So for a problem of such, which involves such large number of physical quantities, it is very difficult. Okay, it is very difficult, and you might sometimes encounter, and in not sometimes actually, whenever you are dealing with such big number of huge number of variables, often you come across with indeterminate systems. Okay, at the end of the day, what we are doing, we are solving system of linear equation. Okay, we are solving system of linear equations. In this particular case, we will be guessing, we'll be solving a system of linear equations to obtain the value of a, b, c and d. Okay, so when the number of variables is large, okay, when the number of variables is large, you often come across indeterminate systems. Okay, now what is indeterminate system? Say a system of linear equation we are defining as ax equal to b. Okay, now ax equal to b, to obtain a solution, okay, say n, a is a n by n matrix. Okay, a is a n by n matrix, and x is a vector, b is a vector. What is the dimension of this vector x? So this is say n by, for this to be n by n, okay, this should be, if you are able to multiply this, say there are x1, x2, xn number of variables, so this should be n by 1, and b is also n by 1. Okay, so suppose this is not matching. Suppose you have a system where there is n by n system, or these are not matching. So in these cases we call it, now see, in this case all the n, the dimensions, okay, n by n, n by 1, n by 1. But suppose you have a system where this is m by n, or this is n by n, this is m by 1, or this is m by 1, then what happens? We say that the system is indeterminate. Okay, indeterminate. Now there are some approximate techniques for solving this sort of system of equations as well, but for getting an exact solution, okay, or determinate system, this condition must be strictly satisfied. So if the number of variables, is too large, then your system may not be determinate always. And that's why for large number of variables or physical phenomena or fluid flow situations where the number of variables, that is both dependent and independent variables, is very large, we prefer Buckingham's pi theorem. So let's see the solution to this problem. So Fd, okay, drag force is a function of diameter d, velocity v, density rho, and coefficient of viscosity mu. Now Fd, as we have seen, Fd if is directly proportional to d to the power a, v to the power b, rho to the power c, mu to the power t. And you can replace the proportionality sign with a equal to sign provided you multiply it with a proportionality constant, which is a number, a real number. Now the dimensions, okay, the dimensions. Now see, in this case, now let me come to the disadvantage of Rayleigh's method. Okay, see, if we write this equation, okay, if you write this equation, so how many unknowns are there? A, B, C, D. Okay, how many unknowns are there? A, B, C, D. So basically there are 4 unknowns, and for getting a determinate form, to obtain the value of these 4 unknowns, how many equations do you require? How many equations do you need? Anyone? There are 4 unknowns, so how many equations do we require?
Four equations.
Yeah, 4 number of equations. Now, if we completely decompose these variables in terms of their fundamental dimensions, okay, that is m, l, and t, are you getting 4 number of equations? Are we getting 4 number of equations?
No, only three.
Only 3, yeah. So that is the problem. Okay, so that is the problem. So that's why Rayleigh's method is suitable only when the number of variables are very less. Okay. Now, but in this problem, how it has been done? Here force F has been considered as a fundamental unit. Okay. So by considering force F as a fundamental unit along with length and time, what we have done, based on this A, B, and C and D, see, A, B, C, and D force. So equating the power, so F is equal to D, D is L, L to the power A, V, LT minus 1 V. Density in terms of force. Okay, density has been written in terms of force. Okay, and viscosity has been written in terms of force. Okay, Newton second per meter square. Now, see, here also the problem is we are getting, there are 3 equations and 4 unknowns. Okay, 3 equations and 4 unknowns. So in an approximate manner, so this is basically a technique for solving a indeterminate system. 3 variables can be expressed in the terms of 4. Okay, 3 variables are expressed in terms of 4. So what they have done, there are 3 equations. So from the first equation, C is equal to 1 minus D. From the third equation, what is the value of B? B is equal to 2C plus D. Putting the value of C in this equation, we are getting 2 minus D. And what is A? From second equation, minus of B plus 4C minus twice D. So the value of A is 2 minus D. So basically, A, B, and C are converted, okay, in terms of, or are represented in terms of D only. Now in this particular question, this has become possible. Okay, every time it may not be possible. So this particular problem was taken for today's session, in today's session, just to illustrate this fact that Rayleigh's method, what are the limitations or disadvantages of Rayleigh's method. Now once all these 3, C, B, and A, are converted in terms of D, you put the values here, okay, in this equation, and you solve for the value of D. Okay, and the answer is Fd rho d square v square function. See, the final answer, as I always tell, the final answer is not important, but the procedure is very important. And this particular problem, the reason behind the discussion of this problem was to illustrate or highlight the limitation of Rayleigh's method. And I hope it is clear. Any doubt? Is it clear? Why? What are the limitations of relic method?
Yes.
Yeah, fine. So see, the first problem that we have discussed, that was related to the principle of dimensional homogeneity. Then the second problem basically deals with Rayleigh's method with special emphasis on what are the limitation of the Rayleigh's method. Now let's move to the third problem, which is basically based on what? There is a resistance force F of a ship, and it is a function of length L, velocity V, acceleration due to gravity G, and fluid properties like density rho and viscosity mu. You have to write this relationship in a dimensionless form. Okay, you have to write this relationship in a dimensionless form. So, if you want to write this in dimensionless form, which method you will apply? So, we have seen that there is Buckingham's pi theorem. Okay, so just give me a second. My lap charge. Yeah, just 1 second. Yeah. So basically, the F. Now, what is F here? F is the resistance force. So F is basically a force. Now, F is a function of length L, velocity V, acceleration due to gravity G, density rho, and coefficient of viscosity mu. So, see, there are 5 number of independent variables and 1 dependent variable, that is force. Okay. Now, we can also attempt this problem with by following Rayleigh's method, but we have already seen since the number of variables is quite large here, Rayleigh's method is not at all a suitable method or method of choice for this problem. So, we will follow Buckingham pi theorem. Now, just in at the beginning of today's session, we have seen. So, what does Buckingham pi theorem states? Buckingham pi theorem. Buckingham pi theorem states that if there is a physical phenomena which is controlled or governed by n number of variables, including both dependent as well as independent variables, and there are m number of fundamental dimensions involved, then uh, that particular system can be represented by n minus m number of dimensionless terms, okay, or which are known as pi terms. And for that, we need to select repeating variables, and the number of repeating variables should be equal to the number of fundamental dimensions involved in the problem. Okay. So first of all, what is the total number of what is the total number of variables in this problem? Force, length, velocity, acceleration due to gravity, density mu. So 1, 2, 3, 4, 5, 6. Okay. So in total, 6 variables are there. Now if you list the fundamental dimensions, okay, if you list all the variables in terms of the fundamental dimensions, we see that the fundamental dimensions for this problem are m, l and t. So it is 3. So how many pi terms? N minus m, that is 6 minus 3 equal to 3 dimensionless or pi terms are sufficient for representing this system. But for that, we need to select 3 number of repeating variables. Now, for the selection of repeating variables, we have seen there are 3 thumb rules. So the first rule is the most important. You cannot choose the dependent variable as you cannot choose the dependent variable, that is f, as the repeating variable. Now out of L, V, 0 and U, you have to select the repeating variables in such a way that it contains all the fundamental dimensions, that is m, l and t. And what is the fundamental rule? If in a problem, if it is possible, okay, it may not be possible in all situations, one length dimension, one velocity dimension and one density. So here length, velocity and density are chosen as repeating variable. Okay, so the first pi term whose dimension, definitely it is a dimensionless term, so m0, l0, t0. Okay, so if you select L, V and rho, then the remaining terms that are left are F, G and mu. Okay, so F first, non-repeating variable F, LA, VV, rho C. So here we can see that M0, L0, T0 when equated with, this is the dimension of the pi term, the first pi term, that is pi 1, equated with F, L to the power A, V to the power B, rho to the power C, sorry, is, and if you write the fundamental dimensions of all this, okay, you will be getting, there are three unknowns A, B and C, you will be getting three equations and you can very easily obtain the value of these equations, and on the basis of this the first pi term pi 1 is F rho V square L square. Okay, now the second and the third pi term, the second and the third pi term, the second and the third pi term, so will be pi 2, say pi 2 will be, what are the repeating variables left? F we have already, non-repeating variables left, F we have already considered, so G and mu, so it will be G V A or A1 rho B1, and what else was there, length C1. Okay, and what will be pi 3? Pi 3 will be mu V A2 rho B2 L C2. So please obtain the value of A1 B1 C1 and A2 B2 and C2. Please obtain the value and tell me what are the next two pi terms. So there are three pi terms. One pi term we have already seen what is that pi term, and what are the other two pi terms, you please calculate and tell me.
काय करू सांग आता मी तू आडवं बोलतेस सगळं ते पुढचं 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 बोलतेस हाय ती सध्या परिस्थितीचा विचार करत नाहीस बघ जरा. पुढच्याला कोण बघायला कोण हे केले पुढचं कोणी सांगितले काय आजचा दिवस कसा आहे हे करायचं बघायचं. तुला काय सांगितले मी 5 लाख रुपये ती मिटवायचं असलं तरी आहे नाहीतर येऊ नको म्हणून सांग ते बापूला फोन करून सांग मला बापू म्हणाल तर मिटवायचं आहे असं असं म्हणतो बापू येणार आहे विचारायला काय सांगू म्हणायचं भाऊजीच विचारायला येणार.
I'm sorry, sir. Sorry.
Yes, sir. Okay, so pi, second pi term G LA VB rho C. So if you obtain the values of A1 B1 and C, A1 B1 and C1 or ABC in this case, it will be GL by V square, and pi 3 similarly will be mu by L V rho. So see, this is the advantage of Buckingham's pi theorem. You can see that the number of variables here is much higher than the number of variables in the previous problem, but still every time we have solved basically three system of linear equations, system of linear equations, and the number of equations and the number of unknowns were same every time. So the systems were determinate. So that is the reason why Buckingham's pi theorem is so popular. So is it clear? Any doubt? Okay.
No, that's it's clear.
So let's move to, so basically how you can express this, the term which contains the dependent variable, the dimensionless term, that can be represented as a function of the other two pi terms. Okay, so the first pi term contained the dependent variable force. So this is the first pi term. So since it contained the dependent variable, it is the force, that is the force. So it can be represented as a function of GL by V square mu by rho VL. Now here, as you can see, V square by GL, V square by GL is nothing but, what is V by square root of GL? It is Froude number. So, and rho VL by mu is Reynolds number. So this can be represented as a function of Froude number and Reynolds number. Anyways, that part is not so significant. But let's move to the next problem. Now next problem, for Froude model law. Okay, so for Froude model law, find the ratios of velocity, discharge, force, work and power in terms of the length scale. So this is Froude's model law. Now, what is the essence behind the Froude's model law? The Froude's model law states that the Froude number of the model and the Froude number of the prototype for which you are testing the model, these two are same. Okay, so similarly we have Reynolds model law, we have Weber's model law. So depending upon the flow situation, you have to decide which model law is valid. Now here in the question itself, it is given that for Froude model law, you have to obtain general expressions for velocity ratio, discharge ratio, force ratio, work ratio and power ratio in terms of the length scale. Okay, in terms of the length scale. Now Froude model law. So Froude number of the model can be written as velocity of the model, G, length scale of the model, is equal to the Froude number of the prototype, Vp, G, L, P. Okay. Now, from this, what you can get? Now, what is LR or the length ratio? Length ratio is the ratio of the length of the model to the length of the prototype. So, what will be LR? From this, LR will be, so we have seen that Vm, this can be written as Vm square root of Lm is equal to Vp divided by square root of Lp. Okay, or square root of Lm by Lp, square root of Lm by Lp is equal to Vm by Vp, or square root of Lr is equal to Vr, that is the velocity ratio, or Lr is equal to Vr square. Okay, so this one we have already seen. So the first portion is the velocity ratio. So the velocity ratio Vr is equal to square root of Lr or Lr to the power of half. Okay, so similarly we have to obtain the discharge ratio, the force ratio, the work ratio and the power ratio, all in terms of the length scale. Okay, length scale or the length ratio. So let's see. So as I have already told, Froude number of the model should be equal to the Froude number of the prototype. That is the Froude model law. Now, acceleration due to gravity G, it's a universal constant. So it is same for both the model and the prototype. So it will be G only. and the length ratio LR is LM by LP, and the density ratio rho R is rho M by rho P. Anyways, so velocity ratio VR, this we have already seen is square root of LR. Okay. Now, what is discharge ratio? Now, discharge ratio, see what is discharge? Discharge is Q is equal to area into velocity. Okay. Now, dimensionally, if you write in terms of ratio, so QR will be equal to velocity ratio into AR. Now, area is nothing but the square of the length ratio. So, VR LR square. Now, what is VR? VR we have already seen, it's LR to the power of half. So, what will be QR? QR will be LR half plus 2. So, that is 5 by 2. Sorry. What is force ratio? Now, force is what? Or the rate of change of momentum. It's basically rho in terms of discharge and velocity is rho QV. So, in terms of density, rho R QR VR. Now QR in terms of LR is LR 5 by 2, VR in terms of LR is LR half, and this multiplied by rho R. So rho R LR 3. Okay. Then work ratio. Work is force into distance ratio. Okay. So what is work done? Work done is the dot product of the force and the displacement. Okay. So in the scalar form, okay, means if you write only in terms of magnitude, or if you want to check the dimensions, then it is force into some distance. Okay, scalar force multiplied in the scalar way with the distance. So force rho r LR cube and distance is LR, so rho r LR 4. And similarly power is equal to force into velocity. So force into velocity is PR. So force is rho r LR cube and velocity is LR half. So LR 7 by 2. So this is a typical example of problems on Froude model law. Similar expressions or ratios can be obtained for Reynolds model law, Weber's model law, Euler's model law. Okay, so this is just for your clarification. Next, let us take this problem. Oil of density 917 kg per meter cube and dynamic viscosity 0.29 Pascal second flows in a pipe of diameter 15 centimeter at a velocity of 2 meter per second. Okay. What would be the velocity of flow of water in a 1 centimeter diameter pipe to make the two flows dynamically similar? Okay. The density and viscosity of water can be taken as 998 kg per meter cube and 1.31 into 10 to the power minus 3 Pascal second respectively. Okay. So, there are two situations. There are two situations. In the first situation, it is given that there is an oil whose density is 917 kg per meter cube and dynamic viscosity is 0.29 Pascal second, and it is flowing in a pipe. Okay, it is flowing in a pipe whose diameter is, so this is the oil, it is flowing in a pipe whose diameter is 15 centimeter and the velocity is 2 meter per second. And in the second situation, velocity of flow in a water, there is a smaller pipe, sorry, the diameter of the other pipe here, this is 15 centimeter, okay, and then water is flowing in a smaller pipe whose diameter is 1 centimeter and yeah, only this much is given, and you need to find the velocity here. Okay, you need to find the velocity here, the velocity of water here. Water is flowing in this pipe. Okay, the condition that is given to you that these two, the flow in these two pipes are dynamically similar. Okay, the flow in these two pipes are dynamically similar. Okay, now if the flow is dynamically similar, it means that some model law is applicable. So the first question is, you have to identify which model law you have to apply, whether it is Froude model law or Reynolds model law or Weber model law or whatever model law. So that is the first part. So can anyone tell me which model law is valid here in this case? Okay. Let us look carefully. The parameters in case of oil.
Reynolds model law.
Yeah, it's Reynolds model. Yeah, good. So how it is Reynolds model law? Let us look at the parameters. For the case of oil, density is given, velocity is given, mu is given, and the diameter of the pipe is given. Okay. In case of water, density is given, mu is given, d is given, and velocity is unknown. Now, if you look at the parameters, okay, rho, v, u, and d. So, which dimensionless numbers? It is Reynolds number, flow Reynolds number in a pipe, rho, v, d by mu. Okay. So, all the parameters are there. So, it is basically the Reynolds number, the Reynolds model law. So, you can choose any one of this as the model and the other one is the prototype. That is not important because here nothing is given, and anyhow if the Reynolds model law is valid, okay, if you select Reynolds model law, then it states that the Reynolds number of the model and the Reynolds number of the prototype must be same. Okay, so in this case we have Reynolds number for the oil case must be equal to the Reynolds number of the water case. Why? Because it is given in the question that they are dynamically similar. So if that is the case, can you please compute and tell me what is the value of the flow velocity in case of water flowing in a pipe of 1 centimeter diameter? So can you compute the answer and tell me? Anyone has obtained the answer? So what will be the Reynolds number of the oil? Rho of the oil, velocity of the oil flow, diameter of the pipe through which the oil is flowing, divided by the viscosity of the oil, and the Reynolds number of the water, density of the water.
Is it 0.18?
Yeah, let's see. Yeah, fine. Let's see. See, I'm not sure about this answer. Okay, but if you followed the same procedure, let's see. Rho W, VW we need to calculate. dW is known, and mu W is given to you. Now, if you look here, Reynolds number VD VD, this is new, that is the kinematic viscosity. Okay, and PdP by mu. Now, velocity ratio Vm by Vp. Okay, so this is the same thing, but they are doing it in the here it has been done in a little bit of only the representation is different. So you can recheck your calculations. Even I will recheck this answer, but the procedure is this only. Okay. Now, what is the density of the oil? The density of the oil is 917. So 917 rho. Velocity of the oil is 2 meter per second. The diameter is 15 centimeters, so it will be 0.15 meter divided by the viscosity is 0.29, that is mu, and this is equal to density of water has been given as 998 into the velocity of water, that is the unknown. The diameter is 1 centimeter, so 0.01 divided by mu, which is 1.31 into 10 to the power minus 3. Okay, so let's see. So 917 into 0.15 divided by 0.29, it's coming as approximately 948.62 is equal to 998 0.01 then divided by 1.31. So it is 7618.32 B. So finally, what will be V? 948.62 divided by 7618.32. So 0.1245. So this answer seems to be correct. That is given here 0.1246. Yes. So it is 0.1246 meter per second. Anyways, there might be some small calculation error, but the procedure, what is important is the procedure should be clear. Now, if you summarize today's session, so it was basically based
Yeah, I
on
got the same answer. I was mistaken.
okay, fine.
Yeah, thank you.
Thank you. So today's session was basically based on the dimensional analysis, and as at the beginning we have discussed about Buckingham Pi theorem, which I am repeating. It's very important. and especially in some situations I have seen students getting confused. Now, the first of all, that the first thing that you need to remember about Buckingham's pi theorem is that the statement of the Buckingham's pi theorem. So it states that if there is a problem which has n number of variables, okay, including both dependent as well as independent variables, and all these variables can be expressed in terms of m number of fundamental dimensions, then that system can be described by n minus m number of dimensionless terms, which are known as pi terms. The second part of Buckingham's pi theorem, and the most confusing part, is how to select the repeating variables. So for selecting the repeating variables, there are certain rules. The first rule is you never select the dependent variable as the repeating variable. The second rule is the repeating variables must be so chosen, okay, the repeating variables must be so chosen that all the fundamental dimensions, okay, that are relevant to that problem under consideration must be contained within these repeated variables, okay. It's not that a single repeating variable should contain all the three. Even the combination means all the m number of repeating variables together should contain all the fundamental dimensions. And thirdly, if typically in the problem there is a variable, there is a velocity variable, there is a length variable, and there is a density variable, then density, velocity, and length is a very good combination of repeating variables. Then the first problem basically explained the importance, that is the most fundamental thing of dimensional analysis, the principle of dimensional homogeneity, which states that the dimensional formula for the left hand side and the right hand side are same. So that was the reason behind discussing the first problem, which is a very simple problem. Then we discussed a problem on Rayleigh's method with the intention of highlighting the limitation of Rayleigh's method. And after that, we moved to the next problem, problem which was based on Buckingham's pi theorem. Okay. Then we have seen one problem on Froude model laws, and then we have seen one problem on Reynolds model law. Now, then what are the problems that are important? What are the problems that are important for from this particular section? Why I am stressing in this section? Because dimensional analysis is a very scoring section. Okay, very scoring section. So the first thing that you need to see is Buckingham pi theorem. Then dimensional similarity. Okay, it may be dynamic similarity, it may be geometric similarity, or it may be kinematic similarity, but dimensional similarity. Then we have the model, before model laws we have the non-dimensional numbers, and after that we have the model laws. So these things are very important. There is no need to give much stress on Rayleigh's method, because Rayleigh's method, it's there in the curriculum. However, because of its limitation, it is not of much use, and in competitive exams, it's very rare that you will be getting any question on Rayleigh's method. However, Buckingham pi theorem, dimensional similarity, non-dimensional numbers, different non-dimensional numbers, and the model laws. These are the four important topics from this chapter. So you should give like stress on these four topics from dimension analysis, and that will solve the purpose. So I hope this was clear. Let's stop, and we'll again meet during next week with some problems and their solution based on the week lecture content of week 8. So thank you very much. So you can please leave the meeting.